Alright, this is NCCER Electrical 4 Revision 3, module number 26410-20, motor operation and maintenance. This should be mostly review stuff for if you've been in electrical for any amount of time. Most of the stuff talking about these motors is going to be review. Like I've said before, teaching electrical classes, or if you haven't heard it yet, the Engineering Mindset on YouTube does really good videos on how motors work and how they're connected and how they're wound and stuff like that. And I recommend for a refresher going back and watching some of those motors or some of those videos and how those motors work, whether they're AC or DC. My first highlight, well, going first into trade terms, like we're gonna talk about different types of insulation classes. I've talked about that before in my electrical classes. You should know what a megometer is, or a megger, or totally enclosed motor. Those are becoming more and more common in industry, especially in like HVAC world with the new refrigerants that are coming out. They're becoming more and more seen in those areas. But my first highlight on page 1 is the second sentence on the page. The life expectancy of a squirrel cage induction motor depends largely on the condition of its insulation, which should be suitable for the operating requirements along with the performance of any required maintenance. So everybody, like if you're looking at this motor right here, everybody looks in here and you can actually see your stator windings in here, and it looks like just a bunch of copper. This is not just a bunch of copper. They are copper windings, which are insulated from each other with a glass-like insulation. It's not glass-like, but it's clear. But they, the hotter this stuff gets, the more that insulation is degraded over time. So how you use this motor largely determines how long it will last. Causes of motor failure, 110. Right hand side of page 1, still in that worn or tight bearings bullet point. But on the right hand side, the first full sentence on the right hand side of page 1. When bearings begin to fail, the condition can be detected by periodically checking the motor for excessive heat, noise, or vibration at the bearing before damage occurs. I know when I worked at Goodyear, I worked in the powerhouse, which had the air compressors, the boilers in there. They had very large boilers and air compressors, but I was in charge of doing weekly checks of I had a thermal camera, and I would take pictures of the bearings on the motors of the air compressors and see if they went up or down based on ambient temperature, and just to see if there was any indication of a bad bearing or a bearing that was going bad, and I was able to find at least a couple, or at least a trend on one motor and how the bearings were working. So watching the temperature of the bearings is a pretty good giveaway of how good the bearing is doing. You've also got vibration, moisture, dust and dirt, insulation deterioration like I was talking about before. Moving on to page 2, I've got the overloading section highlighted. Overloading a motor can cause overheating and eventual bearing failure or premature insulation failure of the windings. Overloading usually occurs because the driven load has been changed to accommodate a higher capacity, heavier capacity, or increased duty cycle. When the driven loads are altered for these reasons, existing motors must be evaluated to be certain they can withstand the new load. Immediate next bullet point, single phasing, first sentence. You'll have a couple of questions come out of that first sentence. The loss of a single phase of a polyphase power source for a running motor can cause the failure of the remaining phase windings, because all the currents flowing through them over the motor if the motor is not protected by proper equipment, i.e. an overload protection. Everybody should know what single phasing is at this point. If you've done the motor control trainer, you lose a leg of power, you're going to be single phasing, and you should know what that noise sounds like in motors. Moving on from there, going on to pages 4 and 5, they do a lot of pictures on 3 and 4 showing different short turns, face-to-face, shorts, stuff like that. I would take time and look through those pictures. But going into 120 motor characteristics, I've got some highlights in 121. 121 motor service connections. I've got the sentence before the bullet points highlighted. NEMA usual service conditions. Standard motors will perform in accordance with their ratings. And they have different ratings for different things. My highlight is, I've got the third bullet point highlighted. Voltage variation of not more than 10% of nameplate voltage. You can have a 10% variance of the nameplate voltage. Operations outside these limits are a voltage imbalance. So you can have a voltage variation of 10%, but the imbalance can only be 5%. Can result in overheating or loss of torque and may require the use of a larger motor. So 10% variation, 5% imbalance. Two different things there. Make sure you got them differentiated or just separated in your head. Next bullet point is highlighted. Frequency variation of not more than 5% of nameplate frequency. Usually in the United States we're running at 60 hertz. So 5% of 60 hertz is going to be 3 hertz. So you have to operate somewhere in that range, plus or minus 3 hertz. Operation outside of these limits results in a substantial speed variation and causes both overheating and reduced torque. You have different starting configurations, which we've talked about in the past. You want a motor to start rapidly or at high torque, or there's different things that can do different things for how a motor starts up. Namely, like a normal squirrel cage motor when it starts up has a very high inrush current. But different methods of starting. I do have the second bullet point in the bottom right of page 5, just the first sentence highlighted. Auto transformer starting uses auto transformers to reduce the voltage and current on the first step. So auto transformers can be used to start motors at a reduced voltage and current. Going on to page 6, they have part winding. The last bullet point in that section is highlighted. Part winding starting involves motors with 2 separate winding circuits. So we'll start on one circuit and then run on another. That's highlighted. Then 1, 2, 3 insulation systems. I have 4 highlights on the right hand side of page 6. I've got Class A highlighted, first sentence. Class A insulation systems have a suitable thermal endurance when operated at the limiting Class A temperature of 105 degrees Celsius. I've got Class B, first sentence highlighted. Class B insulation systems have a suitable thermal endurance when operated at the limiting Class B temperature of 130 degrees Celsius. I've got Class F insulation, that highlighted, second sentence. Typical materials for Class F insulation include mica, glass fiber, and other materials, organic and inorganic, with a compatible bonding substances having suitable thermal ability. Next bullet point, also highlighted, Class H insulation, second sentence. Typical materials include mica, glass fibers, silicone elastomer, key in on that one, and the other materials are inorganic or organic with compatible bonding substances, for example, silicone resins having suitable thermal stability. You've got section 1 review, just 2 questions right there on page 6. I'm going to continue on to section 2. Section 2, motor maintenance and requirements. We will talk about, a generator is pretty much a motor used backwards, kind of. Insulation breakdown, we've got a couple highlights in that, and then leakage current as well. 210 motor maintenance requirements, first sentence is highlighted. You have a couple different highlights in the bullet points. The frequency and thoroughness of maintenance and testing of a motor depend on such factors as, I've got the nature of service is a big factor. And then down below the bullet points, I kind of wrote another bullet point and wrote in the brand or the manufacturer of the motor does not matter. It does not matter what the brand is of the motor. All motors will be maintenance and stuff like that. Motor brand is one of the least cared about characteristics of electric motors. Page 8. I've got table 1 highlighted. on page 8, you're going to have 4 questions come out of table 8. I'll give you 2 of them. The tachometer, fourth one down, is going to be used to check the speeds of rotating machinery. And then the third to last one, that stethoscope is used to detect faulty rotating machinery bearings and leaky valves. You'll have a couple more come out of them on the review and module review, but just highlight that table 1 for different tools or equipment that's used with maintaining motors. Moving on to pages 10 and 11. Receiving and storing motors. Motors are usually pretty rugged. Don't take a lot to store them and stuff like that, but they need to be in a dry place, somewhere where they're not going to get a bunch of crap on them. Another thing that's important, in 214, right above that second warning in 214 on page 10, second to last sentence, only the eye bolts on motor frames are intended for lifting motors. So you can see this motor that's on the board. If I zoom in, you can see this eye bolt that screws the top. Most if not all motors have a part where you can screw in an eye bolt and then pick them up and move them around. You're never picking them up by the ends. Like, you're going to damage the bearing picking them up there. Right after that warning, the following is a list of recommendations for proper motor storage. I've got the 4th one highlighted. Rotate the shafts periodically as specified by the motor manufacturer so that they do not remain in the same position all the time. That is to move oil around in the bearings so that the oil and grease, there's not going to be any kind of corrosion built up in the bearings. You just go through however often the maintenance manual says, and you're turning the shaft however much it says to turn the shaft. Motor bearing maintenance 220. Last sentence of 220 is highlighted. A little bit behind. Motors equipped with sealed bearings are much less prone to bearing failure. Sealed bearings work a lot better, but they're not always practical for some motors. 221. Frequency of lubrication. First sentence is highlighted. The frequency of motor lubrication depends not only on the type of bearing, but also on the motor application and service environment. So where your motor is, whether it's around, how often you can get to grease it. A lot of times the motors that I've seen have had automatic greasers on them. The biggest thing for lubrication of a motor is using the right type of grease. You're going to want to make sure that you have, usually this grease is blue in color, and you do not want to mix greases. You want to use the correct type of grease for these motor bearings. And I've seen a lot of auto greasers and stuff like that. But sometimes during downshifts or downturns and stuff like that, that's when motors are getting lubed up, and it is very important. Motors fail way more often on bearing failure than they do on an electrical failure. They go through the lubrication procedures and how to tag stuff and making sure you're writing down when you did it, stuff like that. Checking bearings 223. Right after that warning on page 13, the third sentence is highlighted in that sentence in the bottom left of page 13. If the bearing housing is unusually hot or growling or grinding sound is being emitted from the area of the bearings, one of the bearings is probably nearing failure. Kind of a no-duh situation. On the right-hand side of the page, right after that note, on the right-hand side of page 13, first sentence is highlighted. Motors should also be checked for in-play. That's the shaft of the motor, how much it moves in and out, which is the backward and forward movement of the shaft. I gotta read the rest of the sentence. They go through the steps on how to check for in-play and moving stuff around. But yeah, moving on to page 14 and 15. I've got no... I don't have any highlights on pages 14 or 15, but you can see the different tools that are used to align motors and stuff like that. Motor insulation testing. So this is the actual testing of the wires and the windings of the motors. Still nothing highlighted on page 15, but 231 going into the next page. Insulation resistance test. Like you should have known already, insulation resistance tests are done with megometers or megers. but I've got the second warning on page 17 highlighted. When using an insulation tester, the motor frame must be directly connecting to the building or earth ground. One second. My next highlight is towards the end of page 17. Just the last full sentence on the page. Absorption. Absorption current consists of two components: polarization current and electron drift. Absorption current consists of two components: polarization current and electron drift. So they go through and they talk about like what your current is over time and making sure that your insulation is good, and that's what a megger is going to be used for. But I've got no highlights on pages 18 or 19 or 20 and 21 either. But they just go through and they go through the readings of megger tests. Page 22, 232, determining the polarization index. All right. Polarization index. So, usually you're using polarization indexes for larger motors and stuff, and you're testing the insulation over time. So you need to know on page 22, I've got that in that paragraph right before the equation, I've got the polarization index ratio, PIR. You know what that stands for, but you need to know that the polarization index ratio is the resistance after 10 minutes versus the resistance after 1 minute. So they hold voltage on a cable for 10 minutes and see what the resistance is, and they hold the voltage on a cable for the same cable for 1 minute and they see what the resistance is. Voltage is going to heat up a cable. The hotter a cable is, normally the less resistance it has. So it's seeing what the hold on. I got that backwards. They got the resistance goes up after it's been heated up in insulation that is good. That's what it is. So you want your number to be higher. So you want at least to be the next sentence after that PIR equation is highlighted. The recommended minimum value of polarization index for AC and DC motors is generally in generators is 2. So you want your resistance after 10 minutes to be twice what it is after 1 minute. This is a highlight for a polarization index. Troubleshooting motors. Motors going bad. Always the first thing to check for motors is making sure you have power. They probably won't talk about that, but making sure there's power. The warning talks about disconnecting power, so either way you're going to go into a motor, you're going to have to check for power, whether you're turning it off or making sure that it's on. I do have the shorts, the first sentence of the shorts bullet point in the bottom right of page 22 highlighted. A short occurs when 2 or more windings of separate phases contact each other at a point, creating a path other than the one intended. So like I said, windings have that that clear insulation. If that insulation wears down, they can be connected, and it's a phase-to-phase short. Moving on to page 23, ground coils. My highlight in 242 is right in the middle of that paragraph. A simple test to determine whether or not a ground exists in the winding can be made using a conventional continuity tester. All you're doing is take a continuity tester and going from your coil to your ground and seeing if there's a connection or not. For like if it's a purely grounded coil, there will be a strong connection. That is the end of section 2. You'll have 4 questions on page 24. I'm going to continue on in section 3. Section 3 is going to be motor installation and commissioning guidelines. So this is putting motors in. In my experience as an electrician and instrument tech, usually maintenance is the one replacing the motors. Electricians come in and wire them up, but that's different plant to plant, and depending on whatever field you're in and stuff like that, you might be the person that's doing everything with a motor. But I'm just letting you know, in my experience, I've been the one to test motors and wire them up. But as far as like aligning and putting in a motor, that was always done by the mechanics. Alignment and adjustment, going to 311. I've got kind of a two-part highlight. You got two questions that come out of this highlight. So the first two sentences of 311 are highlighted. The two typical types of couplings used to reduce. Two types of couplings are used to reduce vibration between motors and their loads are shown in Figure 21. One is a jaw type that is sometimes called a Lovejoy coupling. And then if you go to the next paragraph, first sentence goes along with it. The other type of coupling shown in Figure 21 has internal splines in the coupling halves and the flexible insert between them. So you've got the internal splines and the jaw type, two different types of couplings. But the one used for vibration between motors and their loads is definitely the Lovejoy coupling. 312, end play adjustment. That's like what I talked about when the shaft moves in and out. Like you want some of that. But if you are wanting to adjust the end play, then the highlight I have is the second to last sentence on page 25. Shim or reposition, and then tighten the bearings as necessary for adjusting the end play. And you see the couple different types of couplings on the next page or up here on the board. You got the Lovejoy coupling, which is what you use in the lab here if you do the braking lab on the motor trainer, and then you can have the spline coupling down here. Going along with this section, please don't miss this highlight. At the top left of page 27, in-play adjustment applies to large motors with adjustable bearings. So if you have a large motor, your in-play adjustment is done with the adjustable bearings in the motor, not necessarily with the shims. Make sure you get that, mark that one down. You're going to have a couple different things to do on startup for the first time of a motor. They go through the bullet points for their first time startup. I don't have anything else on page 27, but if you're going into page 28, I have a couple of the bullet points coming from the first time startup. The bullet point on page 28 in the bottom left is highlighted: apply power and momentarily bump or start the motor to verify correct rotation. If wrong, again, lock out and tag out the motor and switch 2 phases, then bump the motor again to check. So this is a common way of testing which way the motor is going to turn. So you hook it up, have the turn stuff back on, turn on for and off for the quickest in the quickest amount of time as you can, and you can see which way that motor is going to turn. And if it has to be switched, you can switch phases or switch 2 of the legs going out there. The next bullet point is also highlighted: start the motor and ensure operation is smooth without excessive vibration or noise. If so, run the motor for 1 hour with no load connected. Like this is especially for larger motors. Whenever we would hook them up, we'd turn them on and let them run for a while, and this is like a wear-in period, getting stuff moving before actually connecting it to a load. Coupled startup. So if you have to, once you couple the motor and start it up, you're going to check for certain things. The first few 1, 2, 3, 4 sentences are highlighted in 322. The first coupled startup should be with no load applied to the driven equipment. Apply power and check the operating current in each phase of the motor. Verify the driven equipment is not transmitting excessive vibration back to the motor through coupling or the foundation. Vibration should be minimal. If not, balancing the load, such as a large blower wheel, may be required. If you got a large blower wheel, like they can put weights on that blower wheel and make it to where doesn't have like a counterbalance on it. It doesn't work as something that's vibrating. It balances the wheel. That's all my highlights for This section, you got section 3 review, all my highlights for the chapter. You got the module review on page 31 and 32, supplemental exercise, and then the practice test as well.